Hello, and welcome to Chapter 1, the continuation of Chapter 1, in particular Section 1.4, which deals with functions. Yay! Insert jazz hands here. Okay, so what are the objectives of this section? So first of all, we want to determine whether relations between two variables are functions and use function notation. We are going to find domains of functions, we're going to use functions to model and solve problems, and we're going to evaluate difference quotients. Those of you that come from college math may remember that we went over all of these things, so very excited. Okay, so let's get into it. Functions and function notation. So a lot of things in our life deal with two quantities that are related to each other in some way. Okay, the term for this relationship is literally called a relation. So sometimes in textbooks, relations can be represented by points, just like let's say I have let's see, we want to say kids. Let's say we want to relate kids and parents in my area is Cerritos, in Cerritos, California. We want to list like the number of parents per kid in a house. So, or adults per child in a house. Let's say that's more broad. So, in my house right now, there's 3 to 1, right? And then let's say next door, there might be 1 to 2, or there might be 5 to 3. You just don't know. So that's their relationship. So if I was to plot all those points, or just to write a table showing those points, I could say, okay, this is a relation. It's the way that these two are related. Not necessarily a function. I don't know yet if I can create an equation to describe that relationship, but the more broad term is a relation. So basically anything can be a relation. So in math, relations can often be represented by equations and formulas. Not always, but often. So let's say, for instance, the simple interest earned on 1,000 for 1 year is related to the annual interest R by that formula. I is equal to 1,000 times R. Okay? Because that's how much interest you would gain. So the formula I equals 1,000 R represents a special kind of relation that matches each item from one set with exactly one item from a different set. And this type of relation is called a function. Sorry. So what's the definition of a function? You take two sets, and you can think of a function as like some people call it a mapping, or you can think of it as a vehicle, or you can think of it as, some people have described it as a machine, right? So an F, or a path, right? You can think of it as a path also. You have two sets, let's call them set A and set B, and a function is a relation that assigns to each element X exactly one element Y. So set A, let's say the set of all possible X, the set of all inputs is called the domain of the function F, and the set B we would call the range, because it's the output, okay, the set of all outputs. So of course this is better illustrated with a beautiful picture. Here it is. So let's look at this function which relates the time of day to the temperature. So see here, and that's funny because I don't know about you, but I like to check the weather in the mornings, so just kind of see what I can do, or if I can send my kids out to play and not feel like I'm toasting them. Okay, so the time of day, so we have 1, 2, 3, 4, 5, 6 p.m. That's the domain. Let's say our inputs are just the hours 1 through 6. And the temperature, so in Celsius. Wow, this is really cold, I guess. So we have 9, 13, 15, 12, and 10. So that's the temperature. So at 1 p.m. it was 9 o'clock. At 2 p.m. it was 13 degrees. 9 o'clock, 9 degrees. At 4 p.m. it was 15. At 3 p.m. it was also 15, and so on. So you can represent this function with ordered pairs. Remember, the ordered pair is a set of coordinates, right, in parentheses. So the first coordinate would be the input, the x value, and the second coordinate is the y value, or the output. So let's talk about, so here it is. So like say 1 p.m., 9 degrees, 2 p.m., 13 degrees, 3 p.m., blah, blah, blah. Okay, so and so on. So what are some characteristics of a function from set A to set B? So a function is that every element in A must be matched with an element in B. Now, some elements in B may not be matched with any element in A. So 2 or more elements in A can be matched with the same element, so like same item in B. However, an element in A cannot be matched with 2 different elements in B, which makes sense because if you think of a function as like a mapping, a path, a machine, you know, like we wouldn't put in 2 different inputs and get the same output. You know, I mean, one input and get 2 different outputs. I totally botched that up, sorry. So basically, it's like if you said, you know, let's say you had a blender and you were making a smoothie and you put a banana in there and some milk. Let's say, for instance, I don't know, whatever your favorite smoothie is. And, you know, when you blend it, right, the blender does the same operation every time. It takes your items and it mashes them up and it, you know, gives you some kind of weird puree thing. Now, what if you had put your items in the blender and you hit go expecting to get your items mixed up, but then when you opened it up, all you got was like a solid, you know, cube of jelly or jello. Like, that would be so weird. How would that even make sense? That doesn't make sense, right? You know, blenders don't make cubes of jello, not that I know of. So that's kind of one way to think about it. Okay, so how are some ways to represent functions? We can represent verbally, right, by just talking, a sentence that describes how input variable is related to output. We can do numerically using a table or a list of ordered pairs that match input with output. We can represent a function graphically using points on a graph in the coordinate plane, right? In the Cartesian plane where, you know, horizontal axis represents input and the vertical axis represents output. Not necessarily have to be X and Y, yeah? It could be something else. Who cares what it's called as long as we understand this is the input, this is the output, this is the independent variable, the dependent variable. And then finally, my favorite, algebraically, using an equation in 2 variables. So how do we determine a relation is a function, okay? Well, we need to know whether each input value is matched with exactly one output value, right? When you have an input value that's matched with 2 or more output values, the relation is not a function. So if you were to look at a set of points and the x repeated, but you had different y's for the same x, you would know this is not a function. So let's look at this. So let's determine if this relation represents y as a function of x. So x is the number of representatives from a state, and the output y is the number of senators. So you have your input x. So you have 2. Oh wait, so this is not, this is different. Is this different? Oh yeah, this is a different case, sorry. So number of representatives from a state, and the output y is the number of senators. So let's look into this. And then B, here's another thing to consider. If you have a table and you have, you know, here's your input x, here's your output y, here's your input x, here's your output y. I literally just said, hey, what if the x repeats and you have different y's? Boom, right? We can already probably cancel that out. And then here, is this, so for every single x, so you have -2, 1, 0, 1, and 2, do we have separate y's? And we do, okay? So let's go into it. So the verbal description does describe y as a function of x. It doesn't matter, regardless of whatever x is, the value of y is always 2. such functions are called constant functions. So B, the table does not describe y as a function of x because, like we noticed earlier, the input 2 is matched with 2 different y values. And then C, the graph does describe y as a function of x. Each input value is matched with exactly one output value. So when we represent functions by like sets of ordered pairs, it's common but in discrete mathematics, which is a different branch of math. But however, we're in algebra, we're in pre-calculus, so it's more common to represent functions using equations or formulas involving 2 variables. So this equation, y is equal to x squared, it's one of our favorites. We can read this as y is a function of x. This represents y as a function of x. And here the equation x is the independent and y is the dependent variable. Okay, so just like we said before, this is reiterating. Domain of the function is the set of all values that the independent variable can take on, and the range of the function is a set of all values taken on by y. So sometimes when we use an equation to represent a function, now here's where function notation is going to start coming into play. We sometimes like to name the function, okay? So let's say here, we know, for example, the equation y equals 1 over x squared describes y as a function of x. So instead of the function being called y, let's say we want to call this function f. And then if we call the function we give the function the name f, we can use this notation where the input is x, the output is f evaluated at x, or in other words, we say f of x, and the equation is f of x is equal to 1 minus x squared. So the way that you can think of this f of x here, we read it as the value of f at x, or simply f of x, right? So basically this symbol represents y for a given x, or the output, okay? So when you write y equal f of x, that makes sense because basically this could be always replaced by a y, okay? Or how you know that y is the output, f of x is also the output of the function evaluated x. Okay, so remember f is the name, f by itself is the name, and then f of x is the value of the function at x, okay? It's a little different. So f of x equals, so for example, f of x equals 3 minus 2x has values, function values denoted by f of negative 1, f of 0, f of 2, and so on. If we want to find these values, we just substitute the values into the equation. So it's kind of cool. Function notation is cool because when you say f of negative 1 like this, you're already telling me, in the reader, hey, this is my function. I'm going to plug in negative 1 for x, and whatever this equals to, that's what the function is. The value of the function is at. So let me show you again. So here, so if x is negative 1, when I plug in negative 1 for x, I get this, this is 3 minus 2x. So 3 minus 2 times negative 1, which becomes 3 plus 2, which is 5. So I'm saying, okay, the value of this function f evaluated at negative 1 is equal to 5. That's like a really big mouthful. And you can say that using like 3 symbols, which is really nice. So for x equals 0, so f evaluated at 0, you plug in 0 to your equation and you would get 3. So the value of the function evaluated at 0 is 3, okay? So you're giving off this idea, like you're communicating something, very succinctly. So it's really nice. Like it's just, I don't know, I love it. Okay, so although f is often used as a convenient function name, and x is often used as the independent variable, of course you can use other letters. It could be called whatever you want. F of x is equal to x squared minus 4x plus 7. We could have called this f of t is equal to t squared minus 4t plus 7, and then g of s is equal to s squared minus 4s plus 7. If you notice carefully, these are all the same function, right? They all say the same thing. Like here, hey, whatever my input is, this is what you're going to do. So f is like the rule, right? Or the whatever the name of the function is. It's telling us what to do with the input. Okay, so in this case, it's telling us, okay, take the input, square it, then subtract the product of 4 times the input, and then add 7. Okay, so all that is being told by f right here. Okay, so you can call this a placeholder or a dummy variable. Some people call it dummy variable sometimes. Okay, so the function can be described by whatever you want to, whatever, square, triangle, who cares, right? Now, next time, so the next thing that we want to talk about is a function defined by 2 or more equations over a domain. Now, when I was first introduced to this concept, it was so crazy because I was like, no, what is this? This looks so confusing. It's not confusing, okay? Let's just say that you took one function, another function, and you kind of took a piece of each, okay, and put them together. And that is what we call piecewise defined function. And you might think like, what does that even mean? Okay, so let's say here, so a piecewise function is saying, okay, over a certain domain, I'm going to have a restriction. So here, I have x less than 0 and x greater than or equal to 0 are my range, my domain. For all x less than 0, the function is going to be, for this piece, the function will be x squared plus 1, okay? So that's what it is. So for every value of x less than 0, you're going to define this function using the rules x squared plus 1. Now, for all of the domain, all the values of x greater than or equal to 0, we're going to define this function f of x by the expression x minus 1. Okay, so see how the rules changed a little bit? So it's going to have a funky graph. It's going to have like a graph that kind of goes like this. I don't know if you probably can't see it, but I can take a picture and show you later. But yes, so let's say, for instance, we had a problem where it says evaluate the function when x is equal to -1, 0, and 1. And then we're given this guy. We have to ask ourselves, okay, where in the domain do these independent, these inputs lie? Okay, so here -1 goes into this, right? -1 is less than 0. Okay, that's true. So I'm going to use x squared plus 1 to evaluate -1. So see, the first one, x equals -1 is less than 0. I'm going to use the top one to get f of -1, which is -1 squared plus 1, which is 2. Okay. If x was 0, I would use, and 1, I would use the bottom, right? Because they're both greater than or equal to 0. So I would use x minus 1. So f of 0 is equal to, and then I use the bottom one because 0 tells me, hey, it's in this one. So 0 minus 1, which is -1. And finally, for 1, you would plug it in and get 0. All right, the domain of a function. So the domain of a function can be defined, can be described explicitly, like I just tell you what it is. Okay, or it can be implied by the expression used to define the function. So what's the implied domain? The implied domain is basically like, it's the set of all real numbers. Remember, all real numbers, okay? It's negatives, positives, decimals, fractions, all of that stuff, you know. We have irrationals. Okay, so for what the expression is defined. So let's say, for instance, here you have f of x is equal to 1 over x squared minus 4. Now, the domain, it gets restricted by values that result in dividing by 0. So here, x could be anything it wants, except we never want to divide by 0, right? So if I have x squared minus 4 equals 0, and I solve for x, I get x is equal to plus or minus 2 because I square root the both sides. Because if I plug in negative 2 here, I get 4 minus 4, that's 0, that's a no-no. If I get positive 2, I get 4 minus 4, that's 0, that's a no-no. Okay, so x is plus or minus 2. And these two values are excluded from the domain because we cannot divide by 0. Okay, so what's another common type of implied domain? We could use, like, for instance, here is a square root of x. We cannot square root negative numbers. We cannot take the square root of a negative number. Why? Because what number times itself is equal to negative? Other than of course, imaginary numbers. We're talking about real numbers. We're not talking about we're talking about real. So this applies to all even roots, yeah? So here, the domain excludes x values that result in even roots of negative numbers, okay? Because that does not exist in our world. So this square root of x is defined only for x is greater than or equal to 0. So the domain of this is going to be 0, bracket, because we include 0, all the way to positive infinity, and then we open circle. We never contain infinity because that literally contradicts the concept of infinity. So we always use an open parenthesis to indicate infinity or negative infinity. Okay, so in general, the domain of a function excludes values that will cause division by 0 or result in the even root of a negative number. So let's find the domain of each function, and you have 4 things here. So remember, domain is, so the hint for A is the domain is all the set of all inputs. So that's the hint for A. B, the hint is it could be everything except that. Remember, you cannot divide by 0. For C, the domain can be anything except for, let's see, you got to think about what would make this not make sense, right? This would make this, what can this not be? We don't have negative volume, at least not in this class, right? So, okay. And then here for D, the hint would be that, remember, you can't take the square root of a negative number, so 4 minus 3x has to be greater than or equal to 0. It has to be positive, okay? We force it. So, okay, so I'm pause, maybe just pause the video, try these on your own, okay? And then unpause, and then we can compare answers. So, there you go. Okay, welcome back. This is assuming that you paused. All right, so the domain of f for A, the domain of f consists of all the first coordinates in the set of ordered pairs. So you have -3, -1, 0, 2, and 4, okay? And then for B, which is 1 over x plus 5, remember we can exclude values that yield 0 in the denominator. So the denominator cannot be 0. So basically the domain of G is a set of all real numbers x except for x equals -5. You can also say x does not equal -5, and there it is. Okay, so for C, the function is a volume function, right? It represents the volume of a sphere. The values of radius r must be positive. Okay, so r has to be greater than or equal to 0, or just greater than 0. So the domain is the set of all real numbers r such that r is greater than 0. Okay, so D. This function is defined, since it was square root of 4 minus 3x, square root function, in order to define their domain, you need to take everything that's underneath the square root and set it greater than or equal to 0, okay, and then solve for x. So if you solve for this, you would subtract 4 from both sides and then divide by -3. And when you divide by this -3, you remember you have to flip it. So x has to be less than or equal to 4/3. So the domain would be, it goes all the way to -infinity. You have to open circle it, comma, all the way to 4/3, and then bracket it because you're including it. So you would stop there. So, okay, so just one more thing. Here, remember that the domain can also be applied by the physical context. So, like, for example, this function, the equation itself, you could let r be negative. but the physical context, because it's a volume and because it's a, radius is the distance away from 0, you can't really have, a sphere can't have a negative or a 0 radius. I guess it would just be 0 if you let it be 0. Okay, so let's do a super fun application. Dimensions of a container. So you work in the marketing department of a soft drink company, are experimenting with a new can of iced tea that's slightly narrower and taller than a standard can. For your experimental can, the ratio of height to radius is 4. So you see here, h over r is equal to 4. So let's write the volume of a can as a function of the radius r. And then B, write the volume of a can as a function of the height h. So for A, this is our volume formula, right? It's pi r squared h. But remember that h over r is equal to 4. So if we solve for h, you get 4r, and you just plug that in for h. So v of r could equal 4 pi r cubed, and that's writing v as a function of r. Now, if I wanted to write v as a function of h, well, you guessed it, you would instead substitute r. You would solve your h over r is equal to 4, and then solve it for r, and then plug that in. So r is equal to h over 4, plug that into r, solve this guy, you would get pi h cubed over 16. Okay. And then lastly, one of my favorites, difference quotients. This is really important. You do use this a lot in calculus. So as this is a pre-calculus class, we need to be good about this. And we did go over a few examples in college math, so I'm kind of excited. So remember, so difference quotient is one of the basic definitions in calculus. Use this ratio where you have the function evaluated at x plus h, right, minus the function evaluated at x all over h, where h cannot be 0, and this is a difference quotient. So so let's do an example. So for f of x is equal to x squared minus 4x plus 7, let's find the difference quotient. That's what this is. So here's the difference quotient. So f of x plus h, I'm literally taking x plus h and plugging it into x squared minus 4x plus 7. So that would be, okay, that would be x plus h squared minus 4x plus h plus 7 minus, and then the original f of x, which is just x squared minus 4x plus 7, and that's all over h. Note the proper usage of parentheses, brackets, yeah, and then parentheses to show that you're subtracting the entire function from the first part. I know that might seem like I'm being a little bit sticky, but we're in pre-calculus now, and we cannot have room for simple algebraic mistakes. We have to be very good about making sure that we're correct. Okay, so if you evaluate x plus h squared, you can do box, or you can multiply it by itself, or remember, it's a perfect square trinomial. This becomes x squared plus 2xh plus h squared. Then you would distribute this negative 4. You would get negative 4x minus 4h plus 7. So that's all this. So all this is the first part, this f of x plus h. And now distribute the negative, and you get minus x squared plus 4x minus 7. And then go ahead and do like terms. So this x squared cancels out with this one. This 4x cancels out with this 4x. This 7 cancels out with this 7. Okay, and you're left with 2xh plus h squared minus 4h all over h. So you notice, what's the GCF here on the top? You have a GCF, a greatest common factor of h, just h. So see, because h is here, h is here, h is here. If I factor out this h, I'm left with 2x plus h minus 4 all over h. And what happened, we cancel these out. We cancel these out, and we're left with 2x plus h minus 4, where h cannot be 0. Okay, so let's just summarize some terminology. So function, what did we talk about? We said function is a relationship between two variables such that each independent variable corresponds to exactly one variable, one value of the dependent variable. So so for every input, there exists one output. That means that for every input, there does not exist more than one output. So like x cannot repeat and have different y's. Okay, so then we also talked about function notation, where y is equal to f of x. F is the name of the function, y is the dependent variable or the output, x is the independent variable or the input, and f of x is the value of the function at x. We also talked about domain. The domain of a function is the set of all inputs where the function is defined. All the inputs, all the values of the independent variable, in other words. So if x is in the domain of f, then you can say f is defined at x. If x is not in the domain of f, then f is said to be undefined at x. And so range would be the set of all outputs, okay? Or in other words, you could say the set of all values assumed by the dependent variable, okay? The set of all function values, okay? Implied domain is basically when you define f using an algebraic expression and you don't specify the domain. The implied domain consists of all the real numbers for which the expression is defined. So this is also, you can also think of this as like a restricted domain, because there's some, by just looking at the type of function it is, the type of equation, we know that there's some values that the independent variable cannot take. Okay, and that is it for 1.4. This is your homework, and I will see you on the next video.